I suggest we continue. I'm sorry for the delay of 5 minutes. We will make good for it, I hope. And it's my pleasure to continue actually the second week of teaching. You realize that we are already full throttle, so you had already an exercise group and an exercise sheet. And I would like to ask, just for my interest, who has already finished the sheet that we distributed on the weekend? Did any group already finish the exercise completely? Okay, wonderful. Yeah. And so it's possible to finish them. Maybe for those that finished, how many hours did you spend on finishing it? Was it just the exercise group itself, or were there some hours before who spent more than 10 hours on it until now?
Including getting MATLAB?
No, not including getting MATLAB. Okay, okay, not more than 10, but more than 5. More than 5 hours? Okay. So I will regularly ask these questions. Actually, it will be more interesting next week when everyone has finished the first real sheet, because we want to keep the order of workload, limited. Shouldn't be exceeding 15 hours or something for sure, and hopefully much less. Besides some motivation, we started already with some introductory material that I want to rehearse because it's important for everyone here. If it's getting too loud, we might need to close the windows. But it's, at the moment I think it will work. So, where we are at the moment, we are still in the introduction. We will hopefully finish the introduction today. And in the introduction, we are in the continuous time systems part. So we are at 1.2, continuous time systems. And the general point of view that we will always look at them is something of this form, where we say x dot is equal to f of x and u. There might be a t or not a t, but u is our control, x the state. So that's like the standard form that we really like to look at very often in this lecture. And you remember that we had the linear time invariant systems, which had the specific form x dot equals ax plus bu. So this is just rehearsal. So that was a specific form of this function f. And for this one, we know that we have a global solution guaranteed due to this Picard-Lindelöf theorem with a Lipschitz constant that we had as the matrix norm of A. So these solutions can exponentially grow, but they cannot explode in finite time. For nonlinear systems, this might be a bit different whenever you don't have a global Lipschitz constant. You remember the details, but I don't rehearse all details. What I wanted to discuss today is continue with some preliminaries regarding continuous time systems and how they get transformed to discrete time systems, because very often we will transform them to discrete time. Let me first start by doing something that is a theoretical concept, and this is the concept of zero order hold. And there is a concept related to it that we call the solution map. So the idea of zero order hold, something classical in control, when you have a continuous time system, but you need to apply controls in a digital fashion, then usually you send your control to the system and then you hold it at the constant level for a while until you get the next value of your control. And that's called zero order hold. So very often the control trajectories of a technically operated system are piecewise constant. So this you could also call piecewise constant from our mathematical perspective. And it's piecewise constant controls. So this would be the trajectory u of t, where this is the time axis t. So a staircase function, so to say. By the way, in MATLAB you plot this with the command stairs. So this is a typical assumption that we make for our controls, and it's in some sense, well, not in some sense, in essence, it's a discretization of the controls, which happens in practice in reality most of the time anyway. So now the question is, what do our states do which live in continuous time when we discretize our controls like this? So the states which I plot here into the same system, they will develop in a continuous time fashion, of course. So this would be x of t, because the state is not influenced only by the control, but also by its own dynamics. So it will be some trajectory piece, which in theory is defined. Yeah? And then it can continue here at this point. It's defined on this piece. You remember that due to the fact that here is a jump in the controls, we might have a non-differentiable point of the trajectory at these points, because there's a jump in the derivative, which means that the derivative can be different on the left and on the right, but this doesn't pose any problem. We can just continue simulating our system starting at these points. And so if we now introduce something like a grid, which we could call tk, and this one we could call tk plus 1, then we could denote the states here as x of tk plus 1. This would be that state, right? And here is x of tk. And now we could make a map from this state to that state. That tells us how the system develops from one sample time to the next. And this is a map that we call the solution map that I want to briefly define, and that I want then to compute for LTI systems. So this is what we call an LTI system, linear time invariant. So if you solve an initial value problem that has an initial value, let's say at x0, which is fixed to some value x0, yeah? And then it follows the trajectory f of x, and here u, which I call also u0, yeah? So it's a constant control, while x depends on time. And this holds on a time interval from 0 to maybe delta t. Then this defines a trajectory piece, which I zoom in now. So here's my control. Yeah? So this would be the u0, the constant control. This would be the initial value, x0, and this would be the trajectory piece, xt. So this is an initial value problem. And as an output of this initial value problem, you could generate the endpoint, which is x of delta t. It's the time point at the end of this interval, while this would be x of 0. And x of delta t implicitly will depend only on two things, namely on x0 and on u0. So it will depend on x0 and u0, and the rest is system dynamics. So if you know x0 and u0, then you know the state at the end of this time interval. And that map we call the solution map. I mean, the solution map could be the trajectory, but we are most interested in the terminal value, because that will tell us how we can continue our system dynamics after that time step, because then we can recursively apply it, and this is already the transition to discrete time systems that we will very often make. So what we can do is we can define a discrete time system which basically says I give an index dis, like discrete, which takes an x0 and a u0, and which generates an x plus. Maybe I call it like this, the next one. And this discrete time system is just defined as this solution map x of delta t semicolon x0 and u0. So we can just say the endpoint that we generate here is a map that depends on the initial value and on the piecewise constant control on that interval, and we just give it the name discrete time system. And the beautiful thing is that now, if we have a discrete time system and we know an initial value of a whole trajectory and the controls which are piecewise constant on these sample times delta t, which are always of the same length, if you know this initial value, then you know with this control you can compute this value. With that one you can compute that value, always using this discrete time system. So your discrete time system tells you basically how your system evolves over the whole future. So we can discuss that in a minute when we talk about discrete time systems, but the idea is we can now work with finite numbers due to the fact that we discretize the controls. And I should mention that, of course, this map that I defined here theoretically is something that we either have to pre-compute by analytical means, which we can do for LTI systems, for example, or we need to approximate this with a numerical routine, which we will most of the time do. And that is something we will cover a bit already in the next sheet. Okay. So I wanted to define the solution map for LTI systems. It's something that you know, but I think it's useful to recall a few concepts that maybe sometimes engineers know better, sometimes mathematicians know them better, so that we all are on the same page. So there is, for an LTI system, I don't need to restate it, there's an analytical formula for the trajectory piece that in general reads like this. If I have an x0 and a u0, which I say is the constant control, then I can just represent my state for the LTI system represented by matrix A and B with this exponential map. So we have an exponential of the matrix A times the time t applied to the initial value. And then there is an integral, so this is a formula that you can look up in textbooks, but we could also easily differentiate that and then realize that it satisfies the LTI system equation. And here's an integral where we would start at 0 and we end at t. We have this exponential map again, but it's now the difference between t and tau. And then it's multiplied with the matrix B. And here I have a d tau. And then I multiply this whole thing. This is now a vector valued, it's a matrix. I like to pull out the u0 out of this. And the usual formula it's inside, but it doesn't matter, right? So this formula is a map for an analytical formula that gives us the explicit solution map for the LTI system. And in particular, if you think of it, this is a matrix, right? And this is a matrix. And if the time t is fixed, which it is for a fixed sampling time, then it's even a fixed matrix, all right? So if we look at this, so we can have x of t delta t, x0, u0, then we can easily define a discrete time system, which is just having this matrix for delta t, yeah? And here this other matrix, that is the discrete time matrix for delta t here, when you evaluate that integral for delta t, times u0. So you easily see that the solution map for a linear time invariant system in continuous time directly moves over to a linear time invariant system in discrete time. It's a standard thing. It's nothing too complicated, but it's something that is very useful. So I'm quick, and I want to be quick because most of this content is known to many of you. But if there are questions, you can interrupt me or raise your hand or make some motion with your head to make me slower, because I will rush otherwise. Okay, but if it's okay, yeah, good. Then I continue, and I directly go to the concept of sensitivities. Just to let you know, we will discuss it more in detail later. So if you think of the solution map as we defined it here, this f discrete time, for example, this was defined by an implicit definition where we said the solution pieces exist, and then we could define it. But the question that we could also ask, is this a differentiable function or not? And fortunately, if you look, for example, at this example for LTI systems, this is definitely a differentiable function. I mean, this whole thing that we have here on the right is a differentiable function of x0 and of u0. It's even a linear function, infinitely times differentiable, and all derivatives apart from the first one are 0. So this is directly a differentiable function, and more generally for nonlinear systems, when we have these solution pieces, you can establish that if the function, but this is something I will not formalize here, but I will just give a remark. If f continuous time is differentiable which usually it is, right? So you write some formulas, polynomials or some modeling equations or whatever. Then also the solution map is. And the degree of differentiability turns out to be even the same. So it's a beautiful fact, but it's technically irrelevant as most functions are C infinity anyway, and so the solution map is also C infinity if it exists at this environment. This is all I want to say about sensitivities at this moment. I just wanted to make you aware of this name. What is a sensitivity? It's the derivative of the solution map. So, in the LTI case, we could compute the solution map by just evaluating these interesting metrics, exponentials or integrals. But in the more general case, when we have a nonlinear function, we cannot. And if we want to represent this solution map on a computer, we can not do anything else than discretize our system. And this is something different than the control discretization, because now it's really about the physics of the state. The state evolution itself needs to be discretized as well. And so many of you have heard about numerical integration methods. I will just give a very short sketch. We will dig a bit deeper later. But just to get the main in place so that we can do some things in our first exercises and have fun with MATLAB. I wanted to recall a few concepts from numerical integration. Integration, by the way, is the same as simulation in our context. It's a bit misleading because an integral is just something of this form, right? But when you say numerical integration, you also include the solution of ODEs, which you could also call numerical simulation of ODE, which would be maybe a bit more precise, but commonly people say this is an integrator. And for example, there's one example, the Euler integrator. The Euler integrator is one of the simplest ones. It's not used in practice, but it's nice to present it for an outline. So the Euler integrator says, how can I solve my ODE? I mean, I have t and I have x here, and I know that my trajectory piece, the real one, should satisfy the ODE, which is given by x dot equals f of x, and I omit the u here because it's constant, or maybe I put u constant here to make clear. I'm not interested in the u, so the u could be just constant here. But still, how does the state evolve? And if I'm at the initial point, then I could compute this f. I have the tangent of my trajectory. I can go a piece into this direction, and then I can, at this point, evaluate my trajectory again. It might point in this direction, and then I'm here, and then I'm here, and I always get a kind of derivative, which might look like this. And you see immediately, of course, that this is not the true trajectory, it's an approximation, but you can also guess that if you make your step size small enough, that then it gets a good approximation of the reality. So the idea here is to divide this time interval, which we could call delta t from the beginning, right? So this delta t is the sampling time for the controls, for example, but we could divide it into finer steps of length h. It could be something like delta t divided by, how do I call it here? I think m. And then I can just do a for loop where I say I goes from 1 to m, and then I define x I, maybe I start at 0 and I end with m minus 1. xi plus 1 is equal to xi plus h times f of xi comma u constant, or u0. And if I loop this, then you see that this implicitly, it needs an x0 as an input, and it also needs a u0 as an input. The rest is inside the function, and its output could be, in particular, xm, which would be an approximation of x delta t. Yeah, the terminal value of your trajectory piece, which is this thing here. That would be xm. And it's of course not the same, but it can be similar to the real value. So there are details about it. This Euler method is under quite easy to satisfy assumptions, namely Lipschitz continuity of your function f. This is a stable method, then it's also consistent of order 1. So one can show that the error that is xm minus x of delta t, the true value, that this error goes to is actually of order h. So when you shrink the h, it will get more and more accurate. That sounds like a good thing. So you just make it small enough and you get a good approximation. It sounds like an easy thing. You just evaluate your f m times, right? And then you have your integration result. But of course, evaluating f could be expensive. And if you have to evaluate it 100 times, and another method would give you maybe a better accuracy at only 10 evaluations of f, then you would be happier. So very often you benchmark these methods, or people have benchmarked integration methods, and there are much more efficient methods. And one class which is widely used in optimal control are the so-called explicit Runge-Kutta methods, which I want to not discuss in detail, but I want to give you one example because it's the most widespread and most competitive integrator for the accuracies that human beings usually desire, where you don't see a difference between trajectories usually. Here we see the difference, right? And there's a better efficiency. There is Runge-Kutta of order 4. That's just one method, which we abbreviate RK4. And that's a method we will very widely use because it's widespread, because it's also in benchmark tests very often the one that looks to be is the most efficient. So what do I mean by efficiency? I want to say it's accuracy versus function evaluations. So that's what you really care about in numerical method. And so if you say this is the error, and if you plot the function evaluations, which I call m, and here I plot the error, which I defined here, and maybe I plot it in a logarithmic scale, doubly logarithmic, then an Euler method shows typically such a decay. So the more times you evaluate your function, that means the smaller you make your time step, the more accurate you get. And maybe you have here somewhere 10 to the minus, let's say 8. Here you have 10 to the minus 2, whatever. And now it turns out that the slope of this function is just 1, because it's a first order method. And there are other methods, and this Runge-Kutta of order 4 method is, which I will present in a minute, is one of them, which goes with a slope of 4. So here's minus 1, here's minus 4. So it's a fourth order method. And it turns out that there are other methods which can get even higher slopes, so they get even more faster down, but they are not more efficient in the range where humans actually usually live, and we like accuracies in this order. 1% up to maybe a percent of a percent. So these are the accuracies that human beings usually are interested in. And the accuracies which we are interested in are typically best computed by the Runge-Kutta method. So what does this magic method do? It just, instead of doing this thing, it does something with 4 steps. And I will just bring it very briefly. By the way, maybe I should ask, who has heard about Runge-Kutta methods before? Everyone. So I can be very fast, right? So we just replace that map with a more complicated formula where we have evaluations of k values, where we say k1 is equal to f xi, and I call the control u0, and then I evaluate the f at the point which I can compute from this k1, but I go half a step size into this direction, plus h half in this direction, u0. Then I also take that value itself, which I call k2, and evaluate now the x half in that direction. Sorry, here I forgot the k1. So I go h half into k2 direction, u0. And then at the end I say k4 is equal to the f evaluated at xi. And now I go full step into that direction. H times k3 at u0. And at the end I add everything, so I say xi plus 1 is equal to a sum which is a weighted sum 1 over 6 of this, and this, and the two in the middle are weighted doubly, so I have actually k1 plus 2k2 plus 2k3 plus k4. Very simple formula, and that replaces this part in the loop. And of course it's 4 times as expensive in terms of function evaluations, but by this magic of mixing different evaluations of f, you get this order behavior, and as I said, m, or it could be actually m times 4 for the Runge-Kutta. That's this is a comparable plot, yeah? So you can compare function evaluations. So with this Runge-Kutta method we usually get good accuracies, and very often in this course we will just set m equals to 1. So we do 1 RK4 step per constant control interval. And with that step we are already good for the beginning of this lecture. So we can do a lot of things with just doing one of the Runge-Kutta steps, and we are happy. And now I have a question to you. When we have fixed the steps to m could be 1 for example, and the function f is a differentiable function, is the Runge-Kutta step, or this solution map that we get, is it a differentiable function, and of which order? Simple question. So you have an f which is, for example, 2 times differentiable, not more, 2 times differentiable. How many times differentiable would be the Runge-Kutta step as a function? It's a complicated function, of course. But it's a complicated function which is a concatenation of 2 times differentiable functions. So concatenations of 2 times differentiable functions are 2 times differentiable, right? So you easily see it's reflected what I just said before. In the numerics, it's absolutely straightforward that the amount of differentiability is just inherited from the function f. And that will be an important concept in the context of Casadi and of the computer exercises we do, because we will actually just construct this as a computer function and then tell this tool differentiate it for us. I'm too lazy to actually look at the derivatives. I don't want to see them. I just need to know that they exist, right? And it's easy to verify that a concatenation of this form has a derivative that exists. Okay, so given the fact that you all knew the Runge-Kutta methods, and of course you know much more about them than what we just described, this is the rehearsal on continuous time systems that I wanted to bring. And we can directly jump to discrete time systems from now on. And if you're, so to say, if you want examples for discrete time systems, very often they come from a discretization, and then very often in our exercise we will just do one Runge-Kutta step of a continuous time system. Because it gives us already a good discretization. But after we have done that, we are just living in discrete times. And discrete time systems are the subject of the first part, of the second part of the lecture. So I need to talk a bit about discrete time systems. And also I need to define a bit of notation, because in discrete time systems we directly fix the time grid. We don't actually care about physical time, so we abstract from it. So we don't give it the name t, which would be usually measured in seconds, right? Instead, we have an index. And this index I very often call k, and its element in the natural numbers, or sometimes negative. So anyway, it's integer. And this is then also, we don't use parentheses usually. It's just a matter of taste. Some books do it. So we don't write x of t, but instead we write x subindex k. I want to really point out that if I write x subindex k, this is still a vector. So that can be very quickly misleading. So this is a vector in Rnx. Yeah? It's not the component of a vector or something. It's just a different way. And that way I save a lot of parentheses on the blackboard, and it will improve our legibility, I think. So that's why I do it. And then a discrete time system is just defined as xk plus 1 is equal to f. And now I omit even the wait a moment. So xk uk. And now this f could depend on time, but if I want to make it depend on time, I could just say it gets another index k, right? So it could be a different f every time point. And now I could define it on a time horizon, so I could say k is defined for 0 up to n minus 1. And then what I have, if you want to visualize what I have here, I have just a sequence of states, and now there is nothing in between. I have states x0, x1, and there's a transition between them described by this function f0 in that case. And here's f1, f2. Here would be the function f3 that maps between x3 and x4. Okay? Because it's nice to think of continuous time systems usually, I will very often use controls. If I want to visualize states and controls in one graph, I will still denote them as if they would be piecewise constant on the time intervals between. It's this would be then, for example, u0, and this would be u1 in a visualization. And of course, this is, you can always think of these things as being trajectory pieces, of course. But in discrete time, we are just interested exactly at these sample points, and that's it. And physical time is forgotten. And now I can rigorously define what I already said here at the beginning, namely that if we know the initial value, this x0, and if we know u0, u1 up to un minus 1, then I can define all the other states. And so here what I can define is a definition 1.5, which I call forward simulation. It's completely trivial, but I think I want to just be sure that when I say forward simulation, we all know what I mean, and to make it exact, this is a map. fsim is a map that maps from nx, from the initial value, and from all the controls. So I just say here plus big N times nu. So this is of all the controls together. It maps to all the states of the trajectory, that is R nx, but how many times? Let's say all states that appear, namely the first one, including the last one, so it's n plus 1. So what does this map do? It takes an x0, a u0, up to un minus 1. Yeah, so this could be, maybe I change the index here. So this is xn, this is un minus 1, fn minus 1, and that's xn minus 1, right? So this is now the whole picture. Then I have here the x0, one input, then all these controls, and if I know them, then I can compute that value, then I can compute that value, and at the end I get also this value. So it maps to the whole trajectory. x0 is trivial, but then it also gives you x1 up to xn. So this is what we call the forward simulation. So the fact is that initial value and controls uniquely determine the trajectory in a completely deterministic fashion, and of course we generate this forward simulation by just looping through the discrete time function. So what I want to point out, and this is interesting if you compare discrete and continuous time systems, once you have a discrete time system which is just a function, that means for every value you get another value, a finite value, a function from Rnx into Rnx, or from the input space, of course, into Rnx. if you concatenate that n times, you still get such a function. So it is unique and deterministic and so on, just as long as it is a function. So there is no necessity, nothing like Lipschitz continuity needed or Picard-Lindelöf. It's all not there. Yeah? It's just once you have a function, also the forward simulation will be a deterministic function. Okay? So it's much easier in theory to treat discrete time systems. We discussed already that a specific case are LTI systems. And LTI systems can be particularly easily, we can really easily write down this fsim of x0, u0 up to un minus 1. So how would it be defined? It's easy to do it, so let me do it for the first component. The first component is identity, right? That's clear. The second component, this x1, is something that depends on x0, like this, a x0 plus b u0. So that's also still trivial. The third component, I mean, this was x0, x1. Now the next one will have another dependency of this. This is all multiplied with an a, right? And then there's an a b times u0, and then there is a plus b u1. And it goes on like that. And at the last point, maybe I zoom into this. I make it a bit bigger so we can see it. So it will be a to the power of n times x0 plus a to the power of n minus 1 times b times u0. And then it goes on a to the power of n minus 2, b times u1, until at the very end you have b times un minus 1. And that's the end of that component. So you easily see that this can be written down explicitly by making recursive eliminations of our function. Maybe one interesting fact in this context is the fact that you call a linear time invariant system controllable, or every system you can controllable, if you can start at any point and you can reach any other point with the controls. And this is just the case if the metrics that you get from these entries that you have here, if you concatenate all together, if that spans the whole space, then actually the LTI system is controllable. So it's a side remark. LTI is controllable. That's a definition that is familiar to engineers. If and only if the metrics that we get from, maybe I start by putting this at the beginning, but that, maybe it doesn't matter. I can reorder the variables, so I start with b. That's what is typically done in the engineering literature. AB is the second entry of this matrix, and the last thing is an minus 1 times b has rank nx for, and now that's a technical fact, for n equals nx. So you need to only look at time horizons of length nx. That's a technical fact that I will omit, due to the fact that the rank of this matrix cannot grow anymore when you increase n anyway longer than nx. But then you call such a system controllable, and basically it means that with a smart choice of controls, because this matrix here spans the whole space, you could actually reach any other state. Was this too fast? Or is it still okay? Any details on this controllability matrix desired? It was fast. It's okay? Good. So, then we can directly continue. And I think this is the right moment actually for a break, but maybe before we do the break, I want to open the floor for questions. So, are there questions on this tour de force through discrete time systems in 5 minutes? maybe the bottom line is discrete time systems are anyway much easier. Yeah, they are just concatenations of functions, that's it, right? That's how you can solve them. Very often they come from discretization of ODEs, and there is the big field of numerical simulation, and one good method is the Runge-Kutta form. It's by far not the only one, and we will learn much more elaborate ones later in the continuous time optimal control part. But in order to get a quick start with already systems that are interesting and look exciting, we wanted to introduce Runge-Kutta methods already at this point. And the fact that you all knew about them already shows that this could be made as quick as we did. By the way, I have a question. The Lorentz attractor wasn't done yesterday, right? It's for next week, or is it already? It was already done yesterday. Sorry. Okay, so wonderful. So then you actually already had this in your exercise even. Very happy. So we do a 10-minute break, and then we continue with optimization problem classes and make the switch to the second big part of our lecture. Okay. Are you ready to continue, ladies and gentlemen? Yeah? Okay, so I want to continue with the next and last short review of existing material that is, so to say, something good to know when we start this. And this is section 1.4 on optimization problem classes. Just wanted to mention a few classes so that we get a general idea what is an optimization problem. And we will dig into it much more deeply in the first part of the lecture. But just to make clear what we mean by an optimization problem is something that has a decision variable that we can decide. It has an objective function that we want to minimize or maximize. Typically we minimize here. And it has constraints that should be satisfied. And you remember our initial example of when I started to run here and I wanted to end at the end, right? My decision variable was how much do I accelerate at every moment in my trajectory. My constraint was I want to arrive at the end point without any velocity. And my decision variable, my objective function could have been the time that I need for this whole thing. Yeah? Very loosely speaking. Of course, this can all be quantified once we have a real example. And also once we have the class that we want to refer to. And so first of all, we need to be clear about what spaces we live in. And I want to make the first dividing line. And that is the one between finite and infinite dimensional optimization. So please be aware of that. Finite versus infinite dimensional optimization. That usually refers to the decision variables. I mean, finite, I could call this x. Yeah? Very often we call decision variable x. Objective function, sometimes we could call it f of x. And for the constraints, I leave it at the moment. We have it more specific soon. But if x is element in R, some Rn, then we call it a finite. Yeah? And if x is element in a function space, yeah, some form of infinite dimensional space, then we are in the infinite case. Very loosely speaking. So why do I say this? Because most optimal control problems actually are most naturally stated as infinite dimensional problems. Yeah? When I say I start to run at some point and then I end at another point, in between there's infinitely many time points where I can decide on the acceleration level. So it's actually an infinite dimensional vector. Of course, very often we will discretize it, for example, by assuming piecewise constant controls, and then we bring it into finite dimensions. But at the beginning, it was an infinite dimensional problem. And this is something just to keep in mind. I also want to mention to the experts that there's another class that's called semi-infinite optimization. And that is when you have typically, I mean, something is finite and something is not finite, right? So it's semi-infinite. And typically decision variables are finite, but the constraints, and in particular inequality constraints, are infinite. I say inequality because otherwise we will have overdetermined problems. Yeah. So to give you an example, I could discretize my optimal control problem by saying I have piecewise constant accelerations at every sample time. But I could still say I want to have some constraints. For example, that I don't have a velocity higher than some 10 meters per second. And this velocity I could impose at every time point of the infinitely many time points that I have. When I have infinitely many constraints at every time point, so many, infinitely many, but I have only finite numbers of decision variables. So a semi-infinite optimization is a mixed class between the two, and sometimes it arises very naturally even after we discretized. But I will not dig into that, and typically we will make sure that our things are in finite dimensions very quickly, and that's what we will also treat exclusively in the first part of this lecture. So we make everything as easy as possible in order to go as practical and as far as possible in practice. So continuous versus integer optimization is another dividing line. And that is mostly about the type of decision variables. And I should say that continuous means really what I wrote down, namely x in Rn. Versus integer means the decision variable. And then I call it z very often, just to make it a bit different. And yeah, z is element in some space of integer numbers. Yeah, let's call it z to the power m. So an m-dimensional space. So if I visualize this, then I have x1 here and x2 here, and everything here could be a decision, either here or here. It's infinite. Yeah. For the integer variables, then I have z1 here and z2 here, for example, and I can choose 0, I can choose 1 for one or for both, I can choose 2 for one, but I cannot choose the points in between. So I'm actually searching on a grid. And if you think of it, here I have continuously many choices, here I have finitely many, so it might seem to you as a naive beginner of optimization, or not you, but some other people that are naive beginners, that it's easier to actually solve these problems because you have only finitely many points to check, right? Maybe you have constraints that tell you that you are anywhere in this box, so then here you have only nine choices to evaluate, and the best of them is the optimum, right? Here you have infinitely many. But it turns out that 9, of course, is a very fortunate fact due to the fact that we have 2 dimensions here only. Once you get slightly higher, like 10 variables, you get exponential growth in the number of possibilities, combinatorial growth, and it's getting impossible to check all these possibilities. For the continuous variables, of course, also the space grows even bigger. You get even more choices. Yeah? For the infinite dimension, you get infinitely dimension decision spaces, but you have the possibility to use derivatives, and they can tell you to go down. And because the derivatives are such a beautiful and powerful concept, they allow you to solve some problems, in particular the convex ones, which we will define in a minute, to global optimality with very efficient algorithms. And that is not so easy for integer problems. So the continuous are the easier ones in general. Yeah. And integer optimization very often arises in many practical applications, so it's good to know about it. Our focus will be mostly on that side, continuous. Not only because it's easier, but also because it's more related to convex optimization. I wanted to state already the general continuous optimization class. And there we very often write it like this. So we have an objective function which is just a nice differentiable function. We say x is element in Rn. We write that under our minimization sign, and then we have our constraints subject to. And then I have, for example, equality constraints, functions that should be 0. And I have inequality constraints, functions that should be smaller than 0. By a sign change, you can change from minimization to maximization, or from bigger than 0 to smaller than 0. So that's all no loss of generality. So these are equality constraints, these are inequality constraints, and that's the objective function. And that's the decision variable. And then for integer optimization, everything is the same, apart from that x is replaced by z and Rn is replaced by z to the power of m. And then there's another class which is actually mixing the two. So this one I omit here, this box, because it's trivial, but I can mix the two, and then I get mixed integer optimization. And if I have mixed integer optimization problem, then I have some variables which are reals and some others which are integer. And then I write it like this, minimizing x element in Rn, z element in z, m. My objective function now depends on the integers and on the non-integers, and the same could be for the constraints. I don't say that this is easier. Actually, this is usually considered to be the hardest class, because a lot of the things you cannot even enumerate, like what you could hear, right? You have to do something with derivatives, but then you still have to enumerate, so it can get very messy. But there are many cases where you can solve these problems nice and efficiently. I think I will not mention too many details about them, because I want to proceed quickly to the flesh of the lecture, which starts only in the next part. But I still want to say something about convex and non-convex. And I want to loosely say about it. We will define these concepts soon. So in the continuous world, we can have convex optimization problems. And convex optimization problems are problems which have a convex feasible set and a convex objective function f of x on a convex feasible set. The feasible set is the point of all points that satisfy the constraints. So if you have a convex objective function, this could be a convex function of one variable. This would be x, this is f of x. Then you see on this picture, okay, if there's a point here that is a local minimum, so in this neighborhood there is nothing better, it turns out to be the global optimum. So x star is a local minimum, implies x star is a global minimum. That's the case for all convex problems. It's easy to prove, but that's the case, that's the reason why people love convex optimization problems so much, because it's easy to verify that you have found a local minimum based on local derivative information. So you know when you have a function, nonlinear function, you can differentiate it, you can check some things in its neighborhood, but you can never know what happens somewhere else. But if you know in addition that your function is a convex function, then by just looking at its neighborhood and checking that something is a local minimum, which you can check, you know already it's a global one. And even more important, if you start somewhere and you go down and you have found the deepest point in some valley, then you know it is the deepest point of the whole problem and there is nothing better. So it's a very exciting fact, and it allows us to solve problems to global optimality which are absolutely non-trivial. And when I say non-trivial, I mean in particular the dimensions. So this is, how can I say it? I mean, it's trivial. Convexity is independent of the dimension, right? So you can have a convex optimization problem in 1 million variables, or even in infinite dimensional spaces, convex optimal control problems. And in all these cases, there are good and reliable algorithms to find global minima. Yeah? And in some of the examples I've shown in the motivating videos, I had argued, and there were actually convex optimization problems which had usually like thousands of variables. So we do both, but convex is the thing that we really love, okay? So when you might want to make an optimization scientist happy, then you say, I have a convex optimization problem, and he or she will start to smile. Yeah? Maybe I should say that because convex optimization is so important and so interesting, there are many classes of convex optimization problems that are having special software packages and specialized solvers. And the most widespread are the so-called linear programming solvers, LP. Maybe you've heard about linear programming. That's a convex optimization problem. Then there are the famous class of QP solvers, quadratic programming. I just write down the shorthands because they are widely used. Programming, by the way, stands for optimization, and it's just historical for optimization. Yeah, it's nice because still nowadays people that develop these algorithms, they need to program a lot, so you can call them programming. LP, QP. Then there is another class, and that's less widely known, but second order cont programs, SOCP, or semi-definite programs, SDP, just to give you some ideas, and I think I had not so many others. QCQP, quadratically constrained quadratic programs, QCQP. So all these things have specialized software packages, and in particular these are really large families of solvers that compete with each other and try to be fastest and most efficient. For convex problems only, in high dimension spaces or not so high dimension spaces, so there's a lot of different solvers going on. And maybe I should say for non-convex but continuous, so once you have continuous optimization problems, namely functions f, g, and h which are smooth, but not anything about convexity or linearity or something, then we just have one class of solvers and we call them NLP solvers, nonlinear programming solvers. And most of the exercises we just do with one interior point, some method for this NLP, and one method that we will use a lot in our exercises called IPOpt, it's an NLP solver. I should say, just for the interested user, if you call an NLP with the data of a QP or an LP, so a convex problem, it will give you the globally optimal solution. So in principle, these NLP solvers are more powerful because they can find local minima of anything. And if the problem was a convex one, then you know already that it is also the global one. But of course, it might be not the most efficient method. So if you have a QP, you will solve it faster with a QP solver than with an NLP solver. But in principle, this is a machine that can actually solve these problems, and these problems without any problem. And these classes need specialized solvers because they are non-smooth, so they are not differentiable. So here you need differentiable f, g, and h. So the only thing that we will usually need to solve this type of problem, this is what we usually call an NLP, nonlinear program, is that we need differentiable functions. That's it. And an initial guess, because once you have a differentiable function that's not convex, here is a non-convex function. Yeah, if you start somewhere, you go down, you will probably not find the global minimum, which is here. So these methods also depend on the initial value, where you start your method, and then it will go down, basically. But the details we will see in a minute, and not only in a minute, actually, directly now. I thought I wanted to already go to the heart of the lecture in the next 25 minutes. And the heart of the lecture is just one thing that is due to one of the most famous scientists of all times, who you all know, who is called Isaac Newton. He was a Lucasian professor of, I think, astronomy or something at Cambridge University in 1600 something, forgot the dates exactly, but discovered, among other, the laws of gravity, planetary motion, but also invented a lot of concepts in mathematics. And one of the things that is relevant to us, maybe not his most famous discovery among others, but it was a method that is usually accredited to him, even though it was not exactly like this developed by him. But we call it the Newton's method. And Newton's method is the core of nearly every optimization and also of many simulation algorithms. So it's good to know about Newton's method. And this is the first chapter of the first part. Yeah? So it's chapter 2. And I call it root finding with Newton type method. And Newton type is, of course, something different than just Newton. It's more general. And I want to introduce this difference between Newton's method and Newton type methods directly from the beginning. So Newton's method is like the basis of nearly every algorithm and optimization that we will look at. And it's just aiming at solving a system. So what is the aim? We want to solve a system R, Z equals 0. For a function f, R, I call it R, which is just mapping from one space into another, and they have the same dimensions, and just want to be consistent with the notation in the script. What dimension? I call it n. Rn to Rn. So this is what we want to solve. And we know that this function is differentiable. Yeah. Differentiable. And of course, it's very involved to solve a nonlinear system of equations. I'll just give you an example, just to write down something down. You could have Rz with one component, that would be something like that, to the 16 minus 2. Very simple thing. How do you solve it? Okay, could try to do something with algebraics, but in general this is not accessible. So another example, Rz could be something, why not I make something here is z1 to the power of 4 minus 2. No, minus z2. And here z2 to the power of 4 minus 2. Just as another example. So this is another root finding system. You see that it has two variables, but also two equations. So you can invent many others. But the main point is that these things have also derivatives. So what would be the dr by dz? Here in this case it would be 16 times z to the power of 15, right? And here dr by dz, would be a Jacobian matrix, which would consist of 4 entries. And what would be these 4 entries? These 4 entries I could also write down. And these entries would be 4 times z1 to the power of 3. Here I have minus 1, right? Here I have 0, and here I have 4 times z2 to the power of 3. So just to give you examples of functions. So this is the Jacobian. And the idea of Newton was, even if we cannot immediately see how to solve such a system, sometimes you can do it algebraically. In this case, you could take actually 4 times the square root of 2, and then you would have the solution, right? So it's a bit too trivial. In some more involved cases, you might not be able to do it that way. But what you can always do is, the idea is solve linear systems. Because that's what we are able to do, right? Linear system solving is something you can do easily with Gaussian elimination or whatever. Linear systems are easy. And so we use a Taylor series of our nonlinear function of first order. So what we need is we just say guess zk. So zk is a vector in Rn. Somewhere we got it, and then we say get a new guess, zk plus 1, as solution of rzk plus dz at zk, so evaluated at that point, that's a Jacobian matrix, times z minus zk. This is the Taylor series of R, and we set this Taylor series to 0. And we immediately see that zk plus 1 is given by this z that solves this, which we get by putting this to the other side, multiplying the inverse of this matrix and putting this to the other side. So then we have zk, here, minus dr dz at zk to the power of minus 1 times r zk. So that would be what we do as a Newton's iteration. So that's the idea of Newton, or of Newton's method, to iterate like this, and then we get another dynamic system. And it's easy to see that once this r is actually 0, then there's nothing here. You don't change anymore, and you have a fixed point of it. Yeah, so that's easy. What is less easy to see is that it converges, and under which conditions it converges. What is maybe interesting to look at it is a picture. So if you have the first example here, I have z here. I have this function z to the power of 16 minus 2. So z to the minus 2, here's minus 2. So here, and then I have z to the power of 16. It's growing like that. So that is z to the power of 16 minus 2, which is r of z. And I'm at some point, for example, at this point, here, this could be zk. And at zk, I have a Taylor series, which is just a tangent at this point. And the next iterate will be this point, zk plus 1. So it's easy to get a picture for that. And it turns out that this method contracts quadratically in the neighborhood of a solution. But what is now the idea of a Newton type method? A Newton type method just says a derivative that is not exact might still help us to find a solution. So why don't we allow that this matrix here that we invert is inexact or might be something like a different matrix? So this is, as I said, Newton. It's the exact one. And more general, a Newton type method we just say zk plus 1 is equal to zk minus some matrix mk to the minus 1 times r of zk. With mk approximately equal to the Jacobian, but not necessarily equal. So that is what a general Newton type method does. And so I want to give one example. And the example is the same r that we had before. So I said z to the power of 16 minus 2. But now I set mk, so this mk is a constant, so it's always the same. Just one approximation. And I could choose, and I think, do I have this example? I don't know. Maybe I take 2. Just something. Maybe 2 is not a good one. I would like to take 80. Higher. I could have taken 2, but then it's so nasty to plot it. So if I have now, what's the picture for this? So here I have z, I have my same function. Okay, r of z. What happens if I'm at this point? And which system do I solve if I replace my real derivative with some approximation, which is, in this case, 80? I mean, the real derivative was this thing, but now it's 80. 80 is something with a very high slope, so it means I approximate my derivative with 80. So it's like actually this line. So I'm at this point. I think My solution should be here, and then this would be zk, and this is zk plus 1. Looks, of course, not as nice as before, but now I could evaluate my function again, which would give me this value here. I could use again my derivative, and then I'm here. And I can repeat this procedure, and you will see that I will also converge to the solution. And this without evaluating any derivative at all. So I only evaluated r. So it might be nice. Of course, for one scalar variable, it's not so important, but once you have huge matrices, size 10,000 times 10,000, inverting a matrix and even computing this product is expensive. So you might want to freeze it for some time, or you want to approximate it with some possibilities. So it's really an advantage to choose different things than just the exact Jacobi. And usually these, with the constant one, this will typically, if it converges, converge linearly. And we should define convergence rates before we can prove something about this convergence speed. But I don't want to omit anything. So maybe before I go on, I would like to open the floor for questions. Yes?
Good. If I would take a constant that would be lower than the actual slope, let's say 0.14.
Yes, exactly. Or the 2 that I chose actually at the beginning. Yeah?
There could be a case where you start oscillating.
Yes.
And even diverge.
Absolutely. Yes. Yes. Maybe I should. No, we will prove a theorem on that. When does it converge and when not? But the point is, Newton-type methods can converge or diverge. Newton's method, the exact one, in the vicinity of a solution of a differentiable function, will converge, quadratically even, while these ones will either converge linearly or diverge linearly. I mean, if you have a constant matrix. And the conditions on this are relatively easy to define, but I think we need a bit more mathematics for it. And before we do that, I want to just recall a few definitions of local convergence rates. I mean, maybe I should ask also in the audience, maybe who has heard about Newton's method before? I guess everyone, but yeah, okay. Also multidimensional Newton's method. Yeah, good, because very often it's just in a one-dimension case, which we have here. And then about local convergence speed. So if you have a sequence of numbers that converges to some point, then there's different rates of convergence. Linearly, quadratically, superlinearly. Who has heard about these numbers? These speeds of convergence? Yeah? Okay. We will again repeat them. And I think we can still do that in the remaining part of this lecture. 2.1, local convergence speeds. Now we'll just define a few rates. So you have some numbers. Yeah? Assume zk element in Rn with zk converges to something which we call z star, yeah? For k going to infinity. And so we assume we have something that converges. Then, so this zk, we can sometimes call it k element in Rn. This would be one way to denote the sequence. Is z to converge to z star. And now I should start. How do I number it there? Q linearly. If and only if there exists an index. I should. So that the zk plus 1 iterate minus z star is smaller or equal to some constant c times the disk k minus z star. For all k bigger than k0 and c is smaller than 1. So I should say there exists a k0 and a c smaller than 1 such that this holds for all k bigger than k0. Okay, so that's Q linearly converging. It's quite intuitive. So if you have the point Z star somewhere, yes, this would be Z star, and now you had a ZK here. There's a distance between the two, and then the norm circle around that point would be this thing, and if you multiply this norm circle with a C, then the C is smaller than 0, then it's a smaller circle, and then it just requires that the next iterate, Zk plus 1, for example, could be here, but it needs to be in this circle, so it needs to shrink. Of course, this might at the beginning of our sequence not hold, so that's why we start to require this condition only after some iterates have been done. So there exists a K0, an index, such that for all indices which are higher than this, you get this contraction. And then we have Q superlinearly, which is a bit stronger. Superlinearly, if and only if. Actually, you could even define its Q linearly. So, but I could also directly say there exists a K0. No, I don't even need that. I just impose the condition Zk plus 1 minus Z star smaller than Zk times Zk minus Z star. There exists a sequence Ck so that Ck converges to 0. So then it's actually, the contraction factor is not smaller than 1, but it's actually getting infinitely small. So it's actually getting better and better contraction. And then third thing is Q quadratically. And when does something converge Q quadratically? It converges Q quadratically if there is a square here. So there exists a K0 element in N and an omega, maybe I should call it like in the script. There I call it C. C smaller than infinity. Yeah? So that for all K that are big enough, Z K plus 1 minus Z star is smaller or equal to C times Zk minus Z star to the square. So for all K that are bigger than K0. And so what does it mean? I think what I like more is that I actually even think of this as C times Zk minus Z star. And I make a bracket around this, and then I multiply it with Zk minus Z star. So you see that all these rates are very related to each other. Linear means you just get these shrinking circles, right? Q superlinearly means that the shrinking factor itself converges to 0. And Q quadratically means that the shrinking factor itself converges to 0, but linearly. Yeah, so it's actually, that's why it's quadratic. And so these names just don't mean anything. I mean, they're just definitions, but what really makes a difference is if you look at what sequence converges and how does it look like if you plot the iterates as a function of k. Yeah, so if I look at the iterates as a function of k for linear convergence, and I think the easiest is that I have my index k here and the distance zk minus z star here. Yeah. So linear convergence means that I have something like, for example, if I have half the error in every iteration, right? So then I have a shrinking factor of 1/2. So then I go down by 1/2. Here would be my index k. So this is 1, 2, 3, 4. Here I get a half. Here I get a half again. Here I get a half. Okay. So this is how linear convergence looks like. Yeah, sometimes people call it also exponential. Yeah, I think in some literature I've even found exponential convergence, but don't like to use it. That's what linear convergence looks like. Very often we plot it as a function, we plot the logarithm of the error. And if we plot the logarithm of the error, zk minus z star, then it looks already a bit more interesting, because a division by 2 is a constant in the logarithmic scale, so then we get actually a constant slope for linear convergence. Q linear. So that's Q linear. And Q superlinearly is something that already gets a bit faster here on the slope. Yeah? So this is superlinearly. And Q quadratically is, so to say, even faster. Q quadratically. And it's so super fast that very often, and in practice, so to say, after 6 iterations, you typically have 10 to the minus 16. And then you're at machine precision and you stop iterating. So if you have Q quadratic convergence, very often less than 10 iterations are enough to really get you to the solution. So examples would be for, so if you have z star equals 0, n equals 1, so just one-dimensional examples, then you could think of this, for example. So what is 1/2 to the power of k? Yeah? So this could be a sequence. So that is the sequence that I just plotted here. But you could also have zk equals 0.99 to the power of k. It's also converging, but much, much slower. It's actually 1% better here, 1% better here. So it's still with a linear rate, but with a much lower contraction. And for quadratic convergence, I think the easiest example is zk to the, and now I like to write it this way, 1 divided by 2 to the power of k. And here is the bracket. So it's something that is incredibly smaller once you get k to some reasonable values. So that could be a quadratically converging sequence. One can easily verify that it satisfies. So this is Q linearly. That's okay, that's slow. Yeah, so that's something you don't like in optimization practice. And this would be an example for Q quadratic. I see there is a question. Yes.
I just have a small question.
Yes.
So I think Q linearly is linearly both imply actual convergence, that Q quadratically doesn't necessarily imply convergence.
Yes, true. So because I assume already that I have convergence, I can use that fact. But Q quadratically, actually, once you have convergence, it's sure that this factor at some point gets smaller than 1, and then you, from that moment, it would also ensure convergence. It's a very good remark, and it will come back to the proof of local convergence rates. Mm-hmm. Yeah. So if you're close enough to a solution, quadratically converging methods will really converge nicely, and Newton's method is such a method. So Newton's method works extremely well when you initialize it close to the solution, but it can diverge when you're far from it, unfortunately. I think this is enough for today. I think we made some progress, and next time we will continue with proving a local contraction theorem that tells us when does Newton's method or Newton type method converge. Thank you.